With that, I want to introduce Dennis Kepler. So Dennis is with the Minnesota DNR's Resource Assessment Program, and he's here today to talk to us about forest inventory with LiDAR and what his group has been doing in this area. And so Dennis, I'll turn it over to you.
Okay, thank you, Matt. Everyone can hear me, I assume? Good. So again, my name is Dennis Kepler. I'm with Resource Assessment, and we've been working on an approach to conducting forest inventory using remote sensing technologies, in particular LiDAR. So before I begin, I want to thank Matt for hosting this and the SFEC for hosting this webinar. I also want to thank other folks for this whole project, in particular the funding. LCCMR gave us $800,000 to research this type of work. The Chippewa and the Superior National Forests have given $800,000 also to pitch in to this work, along with new acquisition areas that's in relation to their national forests. And Cass County has given us some money also, $30,000, along with in-kind contributions. I also want to thank supporting folks, the Nature Conservancy and the Minnesota Association of County Commissioners, the U.S. Forest Service, Northern Research Station, and the Fish and Wildlife. They've all supported this endeavor through advocacy. I also want to thank collaborators and contributors in some of their hard work, particularly the University of Minnesota, Alan Eck, Joe Knight, Keith Pelletier, and Trevor Host. Those three have been working very hard on this remote sensing work and helping us get through some of the details on this project. Alan Eck has contributed his knowledge and experience in forest inventory. I also want to thank Cass County, in particular Joshua Stevenson and Kirk Titus, in their efforts in Cass County, which is where this project actually originated. And then again, I want to thank Northland Community and Technical College for their efforts in UAV. In particular, Jonathan Beck and Steve Sorensen, and the multitude of students who have helped us collect data. And lastly, I want to thank Quantum Spatial, Andrew Brenner and Miles Train for their collaboration efforts in acquiring this LiDAR data. And lastly, the resource assessment staff: Jennifer Corcoran, Scott Hillard, Jason Lingenecker, Ram Dio, Ben Jacobson, and all the interns for all their hard work, which none of this could have got done without their efforts. And then I want to give a shout out to Peggy Nelson for her contracting and financial work. So where are we? This presentation will cover our LiDAR inventory project in 5 areas. Particularly why and where are we doing this? What is LiDAR and how are we using it? We'll talk about the field data collection and the UAS portion, and then the LiDAR analysis and the products that we're producing, which the university is helping us dramatically, and then some final steps. So why and where? There are 17.5 million acres of forest land in Minnesota, 15 billion trees if you think of it as individual trees. And the Minnesota DNR manages about 5 million of those acres. And the way that we manage that forest is through an inventory effort called the Cooperative Stand Assessment, which is CSA for short. We inventory about 125,000 acres each year, and it costs around $11 to $12 per acre to inventory that data. The total investment is going to cost somewhere around $1.4 million per year for that 125,000 acres. So what do we use that for? We use it in our planning. You can see here on the right, on top of our CSA stands. This is CSA information in our forest inventory module, which we access, our foresters access and planners access to manage our lands and do assessments and figure out where to cut, how to manage it for wildlife and other things. Within that forest inventory module, or FIM, we have data that's been collected in the field and processed through FIM, and we have attributes that we use for our planning and natural resource management. You can see here that we can pull out a lot of information, and it's based on the entire stand after it's been inventoried. So what are we looking for? What's important? Cover type, stand age is really important for us, and some of that, and then along with a lot of other data that we collect within the crews, but some of that data can be modeled or calculated at a later date. So this type of stand-based inventory, in which we visit every stand and put multiple plots, is becoming very costly. You can see here it's I calculated about $11 per acre, but it's somewhere around 11.5 to $12 per acre for us to inventory this data. We do 125,000 each year, resulting in 20 years plus inventory cycle on our 5 million acres. The point being that we collect data on every stand that we possibly can each year, so we have to go out and look at that stand as much as possible. We have 5 million acres, which means it's going to cost a significant amount of time, and our costs is substantial. We also want to supply data for other agencies and ownerships. So resource managers want and they also need to apply management strategies across a larger multi-ownership area. Some of you may have been hearing all lands approach that agencies have been talking about, the MFRC, Forest Service, DNR, and this type of information that we produce could contribute to that effort. So we want to be able to provide data to other agencies within the state of Minnesota. How do we do that? We can't do that in our current process. So we came up with a thought process or an idea to use new technology to infer what inventory can look like. LiDAR in particular. LiDAR has come down in price substantially. Back in 2009, it was between $2 to $3 to $4 per acre for LiDAR collection. Just recently, we've collected LiDAR to the tune of 50 cents per acre, and that's high density. So it's come down substantially. We've also increased our ability to process data with new computing power. So with the combination of those two things occurring simultaneously, we feel it's time to, or we felt it was time to start using this data in earnest to say something about our forest land. So you can see the metrics that we're looking at. We want to be able to bring our inventory cycle down from 20 years to something like 10 or better. We want to have some information about adjacent ownerships in relation to the DNR. And we want to be able to pull out these metrics, if we can, using LiDAR, and create a detailed forest structure along with providing other information, habitat modeling and the like, for other agencies. So where are we doing this? So the original plan was for 500,000 acres in Cass County, as you can see in yellow here. It was expanded to 628,000 acres through the process of identifying funding and actual cost for LiDAR. We were able to expand that substantially. We were able to include the red area up in Lake County through a grant from Superior National Forest. So what do we want to do? We want to acquire the LiDAR, high density. Our goal was greater than 12 pulse per square meter in those two areas, and then produce what we call stand boundaries or polygons. But can we, our other thought process was, can we produce tree information alongside of that? And then lastly, we have an outreach effort that I'm doing today, and Jennifer Corcoran has been doing quite a bit also, along with other folks. And then this effort, this outreach effort, will just be amplified in the coming months. So why do we pick these areas? Well, part of it is proximity to Grand Rapids, to our office. And the other part is we want to see if we can utilize ownership in such a way to look at it across all ownerships. So we wanted a diverse ownership layer, or a diverse ownership area. And Cass County is fairly diverse, a lot of public land, but there's private land also. And the same thing with Lake County. That was sort of driven by the Superior National Forest emphasis on this area. But as you can see, the ownership is fairly widespread. The other part of this, the other important part of this is cover types. We wanted to see if we can map areas for forest inventory with some diversity in cover type. And both the Cass County and the Lake County areas are fairly diverse, as diverse as it possibly can in Minnesota, without going too much further south. So LiDAR, if there's any questions about the project itself, I'm open to questions at the moment before I get into what is LiDAR and how we're using it.
Hi, Dennis, this is Matt again.
I can't hear you. Let me.
Sorry about that.
Thank you.
This is Matt again. For folks online, if you do have questions for Dennis, again, that chat area in the lower right, enter your question there and send to all panelists, and we can relay that message to Dennis.
Great.
So, thanks.
No questions so far. Thank you. All right, the LiDAR collection. This is just a quick map depicting where we collected the LiDAR data. We wanted to collect it during peak fall color, mainly because we collect our data, our aerial photography data, during peak fall color for species diversity or identification rather. And that is between mid-September and mid-October, which is when this data was collected in 2017. Again, it covers about 728,000 acres, 100,000 in Lake County and 628 in Cass. We were attempting, we wanted to get greater than 12 pulses per square meter, and we got upwards of 30 to 34 pulses per square meter. And along with that, we also were able to collect 4-band imagery with infrared. So what is LiDAR? It's an active sensor for remote sensing technology, and it emits a light. It emits a pulse of light from the sensor, whether you're in a plane or satellite or even on the ground, and it just sends a pulse of light out to a target, and in this case is targeting the surface of the Earth. And when a pulse of light hits something, it reflects back to the sensor, and we identify what that, how long it took for that pulse to get there and back. Thereby, we can create a structure. We can create a 3D map of our target. And in this case, we were looking for tree cover is what we were most interested in. Some quick terminology in LiDAR. We're going to be talking about first returns, second returns, and multiple returns. All that means is when a pulse of light hits something, it reflects back, but possibly not all of that pulse of light is reflected back. So that one pulse could be reflected back multiple times, giving us a structure, giving us a 3D map of that target. In this case, a tree. Traditionally, single pulse linear LiDAR has been used, and that was fine. But we thought we'd look at something new. And so what this linear LiDAR will do is send a single pulse out, and if it hits something, it's reflected back, and it provides a good 3D map also. However, we were looking at something new, and that's called the SPL, single photon LiDAR, in which it is the pulse of light is sent through an array into many small what we call pulses, and it's a circular type of pulse, if you will. So we were looking at it in such a manner that we were hoping that we could penetrate the forest cover a little better than with a single or linear LiDAR. We were hoping that single or SPL would penetrate it a little better. A few more terms in LiDAR. So I'm sorry, let me go back to that single pulse and the SPL. We use the SPL in this project, and not the linear LiDAR. So when LiDAR penetrates a structure or a target, it can records the returns. And in this case, when you see the top picture, there is all returns, and there's 16,000, for instance, pulses in this one clip. We can examine each return independently and identify where in the structure those returns are coming from. So in this case, most of the returns are the first returns, and that can either be the top of a tree, top of a shrub, or the ground if there's no structure over the top of it. And as that pulse of light penetrates the canopy, in this case, multiple returns, second, third, and fourth, in this case, are identified the deeper into the canopy or the further away from the sensor you see. And you can see that the fourth return in this case has diminished substantially to less than 1%. So traditionally, we've used statewide. We have low density LiDAR, which you can see in this rendition. On the left, we have deciduous trees, and on the right, we have coniferous. And the low density LiDAR has been used primarily for topographic purposes, and using it for vegetation purposes has been problematic because, as you can see, really doesn't give a great outline of structures or vegetation. However, if we use high density LiDAR, and in this rendition it's 8 pulse per square meter, you can really see the detail. Deciduous trees really pop out, coniferous trees pop out also. So more definition, more usable data, and we should be able to provide a lot more detail to our forest managers with this kind of information. So this picture is basically depicting height, and white, anything white is higher than the green. This is actual single photon LiDAR data from our collect, and you can see that there is a substantial amount of detail in this picture, and we want to be able to utilize that detail. And this is just another look at it using the 4-band imagery. In this case, it's the natural color. So we were able to colorize the LiDAR data with the imagery, the 30-centimeter imagery that we collected. This is the same area using the color infrared imagery. So you can see that we should be able to say something about the forest land, about the structure, about a stand that exists there, both in species composition, our hope, and in actual inventory information like volumes and such. And along with that, identify what's non-forest and water and other things. So I'll pause here again for any questions, which I don't see any coming in, about our field data collection.
Sorry about that. Dennis, this is Matt again, not seeing any questions.
Okay.
Again, if folks have them, feel free in the chat area, and we'll relay those questions to Dennis. Good.
All right, so I'll move on to field data collection and the use of unmanned aerial systems. In this, I'll show you both the Cass County area and the Lake County area. In the Cass County area, we developed a grid based on some of Alan Eck's imputation processes that he's written up. So what we wanted to be able to do is identify a targeted type of inventory system that we could utilize pretty readily. So we wanted to be able to tie this data directly to the LiDAR data. And so what we wanted to do was identify the type of plot to use. Variable radius plots could cause some problems with that, so we opted for a fixed radius plot, 10th acre fixed radius plot in this case. As you can see that we created 500 points, about 500 points. Each plot represents about 1,200 acres or so. 432 plots were actually completed in the summer of 17 and 18. About 20 interns worked on this project, and that's what we were able to collect. Cass County collected about 59 of those 432 plots. And as you can see in the map, some were inaccessible or not measured because of other situations. In Lake County, we went about it in a little different fashion. We wanted to use the LiDAR data to drive where we will do our inventory. Again, we use the 10th acre fixed radius plots, but we use the LiDAR data to identify potential stands and their cover types, and then go along and provide data that way. We did have a couple of location-based reasons, and that is we want to be able to access these plots easier. That's why you don't see plots scattered throughout the entire area. The boundary waters may have been more difficult to go out and inventory for us. Cost-wise was a big reason. So our fixed radius plot is for our design. We used this plot design along with a sub-meter Trimble R2 GPS unit. We wanted to tie that plot center to the earth as accurately as possible. so that we could then tie that plot and all the trees within that plot to the LiDAR data. So we also used the Mesa Juniper ruggedized table for using Survey 123 for our data collection. So what did we collect? Plot level data with full stem and trees. In 2017, we collected trees 3-inch in diameter and up, and we changed that in 2018 to 5-inch in diameter because we were not really seeing the benefit from that smaller tree count. We weren't seeing it in the LiDAR, so there's no reason to measure it at the moment. So we're looking at this data and what we need to collect. And one really important part of this process was not only to anchor that plot center, but we also need to get an accurate measurement both in distance and azimuth to each tree within that plot so that we could map those trees within the LiDAR data. We also wanted to identify vegetation in the cylinder of the plot. And this is basically in reference to what the LiDAR sees. We want to be able to not only tie, we want to be able to tie the plot to the LiDAR data, and so we wanted to be able to say something about that plot that is concurrent to the LiDAR information. So as you can see here, we collected information in these four areas in conjunction with what we see in LiDAR. And we also took pictures at each plot in the cardinal directions so we can have a clear picture of what is going on in that plot. This includes a straight overhead picture. So again, our plot is a 10th acre plot, 37.2 feet out, and every tree within that plot is measured 5-inch in diameter. In this case, this is a rendition of a LiDAR point cloud clipped to a plot, 10th acre plot, and of course our goal is to tie this field data to the LiDAR data, and we want to be able to label the stands, and our hope is to label individual trees also, but that's yet to be seen. So again, we want to be able to tie that field data directly to that LiDAR data. And I know Ram has been working on this, Ram and Scott, and there has been some challenges to tie in this data directly to the LiDAR data. A lot of it has to do with leaf off conditions. Some of our LiDAR, while we attempted to collect it during full leaf on, we were not always able to collect it during that time. As you might well know, collecting aerial photography and other data in the northern part of Minnesota during a small window of opportunity in the fall can be problematic with weather. So some of the data is actually leaf off, mainly the lowlands, but we did go a little past full leaf cover. So I'll go into how we're using the unmanned aerial systems. Again, we're working with Northland Community and Technical College to collect this data, and we wanted to be able to see if drones or UAS are possible to be used for inventory purposes. So we contracted them to collect data, and as you can see, it's very high resolution data, and we want to be able to again tie a plot to that data and see if we can say something about the information. I saw a question come up, but I couldn't read it fast enough.
Yeah, Dennis, we have one question that, or two questions now that came in. Going back to the different format in Cass County versus Lake County, can you compare and contrast the two approaches for plot locations? That is, what looked like a grid in Cass and a LiDAR-informed process in Lake County.
So we haven't done a full comparison yet. However, I can explain a little bit about some of the reasons why the grid process in Cass County is referenced to Alan X study on imputation. What we wanted to be able to do is go to a plot no matter where the location exists and get as close to that plot as possible to collect the field data. And if we did that over an entire area through a grid process, the assumption or the research shows that you should be able to impute that data fairly accurately. And we wanted to see if that imputation process really holds up in that area. For the Lake County area, we knew that we weren't going to be able to cover the entire LiDAR collection area because of the boundary waters and the cost of collecting that data. So we wanted to identify another methodology in collecting field data in association to LiDAR. So we wanted to attempt to classify the LiDAR fairly generalized so that we can so that we're not collecting multiple plots in the same cover type. We should be able to impute a stand that's similar to another stand, but that we don't have to actually go to the field on. That was our reasoning behind that.
Thanks, Dennis. And another question about the vertical structure measurements you collected. A question just asking, can you talk a little bit more about the data you collected on vertical structure? And I think that was the field measurements of vertical structure.
So we mainly, what we were looking at was what does the structure look like within that stand? Are there shrubs at 3 meters or at let me go back to that. So what we're trying to identify are the structure is the structure within that plot. So there may be shrubs or seedlings or small trees at ground level, and then anything that we can identify vertically as we go up into the canopy of the trees. Excuse me. So as you see here, we wanted to be able to sort out where different types of vegetation exist within that vertical column, and relate it back to the LiDAR data. So of course, overstory and canopy, which is where the predominant returns exist, because that's what the sensor sees. That is an important part of the LiDAR collect, but it's also important to identify how that exists within the structure of the forest, and so on and so forth. Whether we can see those last two, the knee to head high and the knee high, is yet to be seen. We don't know if we're seeing all of that structure in the LiDAR, and in some cases we might be, so it's yet to be determined. I think I saw another question.
Yeah, going back to where you left off on the UAS, did the UAS have LiDAR or just high resolution photography?
No, it did not have LiDAR. It only had high resolution imagery, as you can see here, very high resolution imagery. However, we also were able to collect stereo imagery with the UAS with as much as an 80% overlap, and we were able to process that to create a digital surface model, as you can see here on the right. So that's a digital surface model of the same area using using the stereo imagery. And what that does is it creates a point cloud, and then we use that to create a digital surface model. So it's another way to create a point cloud without using LiDAR. And we can say something about an area using a drone in this manner. Another question?
Okay. Yeah, one other question, then maybe you can move back to your slides, Dennis. Going back to the field measurements within height strata. So within those height strata, did you record just percent cover or other variables, something else?
So when we look at this information here, what we're looking at is the vertical structure, and we were attempting to identify within each one of those structure or strata what that percent cover is. So overstory may be higher crown closure or canopy closure than the mid-story vegetation. So yes, we were attempting to identify and estimate what that closure looked like within the vegetation within each one of these strata or vertical strata.
Thanks, Dennis. No other questions as of now.
All right, so going back to the UAS, again, this is a DSM created from the stereo imagery that was collected from the UAS, and with stereo at that 80% overlap, you can create a point cloud and a DSM, which it can be useful. So again, this is just another rendition of our plot center with the plot boundary, the 10th acre plot, overlaid on our 30 centimeter imagery that we collected during the LiDAR process. And again, this is the data collected, or the imagery collected from the UAS. So you can see that we were trying to identify specific heights above the trees that we could use the UAS for a good depiction of information. So again, plot data. So this is from the UAS. This is what it looks like from the ground, and then in those cardinal directions. So we want to be able to tie all that information to the LiDAR data and say something about that plot. Again, going back to the 30 centimeter imagery that we collected with the LiDAR data, this is the same stuff with FSA, not very useful. However, this is from plot center looking up, and then in the cardinal directions, we want to be able to, and we did this for every plot, all 432 plots that we collected. We took this information, and we are putting it together to tie back to the LiDAR data. So for instance, this is the plot center. This is the actual outline of the plot within the aerial photography, the 30 centimeter CIR, and this is the actual LiDAR data clipped to that 10th acre plot. I don't think that has a moving, no, it doesn't. So that's the field data. That's the field collection and the UAS. Any other questions on that part of the webinar?
I'm not seeing any other questions, Dennis.
Okay, so I'll just move right into the LiDAR analysis and resulting products. So after we collected the LiDAR data, we sent, after our quality assessment, we sent this on to the University of Minnesota, the remote sensing lab with Joe Knight. And we've been working with those folks to output some information that we're looking for, so that we can utilize that data to actually create our inventory of these areas. And so this is just a list of what we have through this process of working with the university in those two areas. So this is what they've completed thus far. They've classified all the stands with symmetrics. They've classified substands or objects, or we can go as far as to say possible trees, individual trees, and we've identified metrics to go along with those objects. And they've done a raster classification with cover type. Yet to be completed is to assign a lowland and upland classes to those substands and stands. They may actually have that done this week or next week. If Keith is online, he can inform us whether they're done with that task or not. That task should be fairly standard, using the new updated NWI, the National Wetlands Inventory data that's been completed. So this is just another rendition of our LiDAR data, and I just wanted to illustrate this to you, to show the detail that we're getting out of this information. You can see some interesting facts that I think are important in this rendition. One is you can see the canopy, because this is leaf on. The LiDAR is not necessarily penetrating fully into the understory. You can see some understory pretty well, but you can't see the bole of the trees very well. And so some modeling efforts are going to be important in this endeavor. Otherwise, this 30 plus posts per square meter has a lot of information, both in the overstory and in openings and structures, and possibly the understory also. So along with the LiDAR data, of course, we have natural color imagery to go along with it, which helps identify species, and then again CIR. So these are the products that have been produced from the LiDAR and imagery collection. We've also collected, or we've also created a digital elevation map, a DEM, that are, in particular, any lake that's greater than 2 acres has been flattened, and all streams that are greater than 100 feet wide are flattened. So you can see that there's some water in here that's been flattened, but a pretty detailed digital elevation model using that high resolution or high definition LiDAR data. The other thing that's been produced is a digital surface model, which is useful in the classification process for height. And this is depicting a lot of information also, because we're getting height above ground with this digital surface model. You can see how it's fairly grainy with that, or coarse with the treetops illustrated here. And then the LAS has been classified based on height also. Another important part of this process is to normalize the point cloud. So the LiDAR is collected, and it's usually above sea level is where they identify those points in relation to where each point exists in space. So we have to normalize it to the ground, so we know the actual height of structures above ground. And that blue, the lower one, you can see that it's been normalized, and we can identify the actual heights above the ground that structure or canopies exist. Another process that helps us in this inventory work is to create a canopy height model that is spike free. So when the LiDAR data is collected, we're looking at the first returns in this case, and you can see that that a lot of spikes exist. So canopies, using the first returns, the canopy is not as smooth as we would like it to be, because it may have been penetrated, the canopy may have been penetrated by one of those pulses, and the first return would have been lower on the tree than we would like. So on the left, you can see that it's not a smooth rendition of a tree or a canopy. So we run the process of spike-free canopy height model, and that gives us a much better rendition of what a canopy looks like. And that is, this approach fills in these areas, and it uses all the returns and the max elevation to help this process. So again, just another illustration of what this canopy height model does, and creating a spike-free rendition in the LiDAR helps us to identify that tree canopy, or the forest canopy, if you will. On the left, of course, is the actual tree, and what it looks like in the first returns on the top right. Pretty difficult to glean good information from that, but if we run it through the spike-free process, we get a much smoother surface and a better rendition of what that tree actually looks like, or the forest canopy. And in this case, it's the forest canopy. So again, first returns identified here, and spike-free process completed. And it'll show a more continuous canopy. As you can see, some of those dark green areas are a better rendition of what a canopy would look like, rather than what its first returns make it appear. So the whole process that the university has used to create our stand polygons, or stands, is an object-based system, and it's running each individual tile, of which there are many. I don't remember how many tiles there are, but there are quite a few. So it's integrating it through a batching process and identifying those objects through a knowledge-based approach, using the LiDAR, the aerial imagery, and other classification processes. It's an iterative approach, which means that we run it through the segmentation and e-cognition, and look at it and continue the segmentation process iteratively, and then we classify it and use use the optical imagery, the LiDAR, and other vector information through that segmentation process. Then we classify it and reshape it based on the morphology, so we can map individual features or groups of features. So this object-based process to create stands is an iterative process in which we use a multi-threshold and multi-resolution process first. As you can see here, this is the actual 30 centimeter imagery used in this segmentation process. Here is the canopy height model of the same area, and we identify through that multi-threshold segmentation what's actually tall and what's on the ground. So this is a canopy height identification of what we see based on height. Then we run through that classification of creating cover types, a multi process, and using the fall and the summer imagery to create a NDVI difference, and then we can identify what's actually coniferous and what's actually deciduous. And you can see here some of the breakdown that we have between what's actually deciduous and coniferous in both of those areas, the Superior and the Chippewa. They're fairly relatively close in coniferous and deciduous. So the next process that the university used is called a watershed process, in which we perform this on all tall classes, which is greater than 1 meter. So the CHM, or the canopy height model layer, is to find the canopy peaks and valleys in the stand. So we use depth, where the range of the values from the canopy height model are used to merge neighboring objects based on the difference between those ranges. So we fill those areas up through an inversion process. So the neighborhood is defined as the 8 pixels surrounding that seed, and that seed is right there. And so each individual tree is identified through that seed and then filled up based on the information in the canopy height model. So as we run through that process of the watershed segmentation, we end up with objects identified here. So you can see that there's a ton of objects in this rendition. A little closer view of those objects is here. If you remember, to the right of that white box, and to the I guess to the southeast of that would be that conifer area, and each individual potential tree is identified as an object. And within each of those objects, we're pulling out these metrics that we can use when we create the stand, or what we can use to say something about that specific object. And lastly, we grow those. And lastly, so what we want to be able to do is use those objects and create stands, because that's how we manage our forest. We don't go by objects. We manage our area based on stands, and so that's what this region grow is going to help us do. In this case, you can see where we grew those objects into a contiguous stand, and you can see that they're separated by types first, deciduous, coniferous, and some of them are multiple. You can identify areas that it worked really well, and some areas that you may have questions about. In particular, there's a couple of stands here that are very heterogeneous, and those could be problematic in our efforts, and so we may need to do a little more work on some of those areas. And again, this is based on the canopy height model, and you can see where the stands grew based on that information also. So we've colorized it here based on height, I believe, and type, and so each one of these stands will contain some of these metrics, or most of these metrics, and others. So we also identify each stand based on the area. So anything less than 5 acres, we've classified as small, and then we grow them and classify them as they get larger. So we have 3 mediums that are important and large. This kind of goes into our premise in the DNR that most of our stands, or the average size of our stand is around 23 to 25 acres in size, and so we want to be able to identify a size within each stand. So this is what the university has produced for us. The stand classification based on size of stand. As you can see here, there are several classes from gaps in the canopy to very large stands that you can see on the left. And again, same thing in the Lake County area, from canopy gaps, or gaps in the canopy, to larger stands in the dark blue. So within these stands, we can pull out quite a bit of information, and you can see here that this is a Trevor Host slide where he's illustrating how we're pulling out information and what we're using that information as. So we want a suite of information from the LiDAR point cloud and the data itself. So in this case, we're looking at what the max height is. We have a max height actually for each individual object in that stand, and now we've grown it to the full stand. So now we know what the height of that stand is. We also know what the median is. We also know what the minimum is, and just all the other information over there that you see, the number of acres and so on. The other important part of this that I don't see listed here, it might be, percent conifer and percent deciduous. That's another important part, that we can identify these right out of the gate. We can identify these polygons as what their cover type is based on whether they're coniferous or deciduous, and what their height is. And we should be able to model forward, or model these to identify some volumes. Few more stand statistics that we can pull out of this information. Not only canopy height, but what is the 95th percentile, standard deviation, and so on and so forth. I don't need to read all these off to you, but there's quite a bit of information that we can utilize when we're running through this process, that we should be able to use in our final analysis for inventory. So again, these are the attributes that we're pulling out of not only the point cloud, but also the individual objects or trees and the individual stands that we have. So you can see here there's quite a bit of information that we have that is very useful in understanding what that stand looks like, and what how we can use it to calculate volumes. Any questions on thus far? This will be the last part of the webinar.
Yes, Dennis, we do have a question going back to the raster classification. One question, at what resolution was the raster classification performed?
That's a good question, and I should be able to answer that. However, I think it's 30-meter resolution is what we, where is that? That's based on the 30 centimeter imagery that we collected alongside the LiDAR data.
Great. And then a second question, have you compared your stands as computed with the current DNR inventory stands?
That's a very good question, and one that we're going to get to in the next several months. That's part of our next step. So we want to be able to compare. It might be problematic to compare directly with what we have in our CSA stands, mainly because the polygons that are created, or the stands that are created through this process, are more biological, whereas our stands that are created through the DNR process are photo interpreted and based on some management scheme or process that they're looking for. So comparing what we currently have to this data is possibly not going to be completed in the next 6 months. But what we want to be able to do is look at how that data can be used in this whole process. During these next steps is we want to be able to identify potential data that we currently have in our CSA data. How can we utilize that information in this in the LiDAR process? So a direct comparison may not happen. I don't see what that said. Looks like Jennifer is trying to say something, but I can't read it. You have something to say, Jennifer?
So Dennis, I'm wondering if you have any more slides, because we have a couple of other questions that have come in.
I have some more slides, but I'll answer questions now, or we can wait till the end. I only have 8 more slides, I think.
Yeah, I wonder if you go ahead and go through those slides, and then we'll save all the questions for the end.
Okay, I'll move through this fairly quick because it looks like we're past the time. So again, we want to tie these plots, our plot data to the LiDAR data, and here's an example of a plot center with each individual tree that has been measured, and how that ties to the imagery. We want to be able to tie that to the LiDAR, and essentially do an assessment uh, whether that object is accurate or not. So the other thing that we're working on, in fact, Ram is the one working on this, is grid metrics, and using those models to create data for other uses like biomass, total volume, and basal area. We also want to be able to, while the university has created data for us, we want to be able to use other software. So we've been coding in R. Actually, not me. Ram and Scott Hillard have been coding in R to see if we can create a segmentation process without using proprietary software. As you can see here, we've done some of that. And again, one of our goals is to create an inventory that costs less than we're currently spending on our inventory. Cover type and stand age is critical, and I think that I've shown that that's probably fairly easy to pull out with LiDAR. And lastly, we are going to do a comprehensive cost-benefit analysis to see how this compares, and if it's reasonable to complete this type of forest inventory using remote sensing based on what we've done. We're also working with the 3D Geomatic Committee and the Geospatial Advisory Council to develop a plan for statewide high-density LiDAR collection. And then this is actually my last one. We have collected some new LiDAR data in 2018. We just completed it in that orange area up in Lake County. There's some overlap with our previous collect. This is linear LiDAR, so it's not SPL or single photon LiDAR. The new data is linear, and it is very high density. Well, we don't know where it is yet, but our criteria was over 18 pulse per square meter. And lastly, I just want to thank all of our collaborators in this endeavor. We're not completed yet. We're supposed to be done in June of 2019, which is 7 months away. But all these folks have put in effort and money and time also. Well, I have Jennifer's name if they're not mine. So questions?
Great, thanks, Dennis. We've got at least 4 questions that I see. If you do have questions, we'll stay on the line and keep relaying them to Dennis. So Dennis, one question about the cost. So do you remember what the cost was for flying the LiDAR?
Yeah, so when the final analysis for the collection of both the LiDAR and the 30 centimeter aerial imagery, 4-band imagery, came out to be about 75 cents per acre. It was a little cheaper in Cass County because it was a larger continuous area, and that was in the 61, I believe, cents per acre, and it was a little more expensive, closer to 80 cents per acre in the Lake County area because it was smaller and in a little more difficult area to access, because of the the proximity to the National Guard Armory in Duluth, their Air Force.
Great. Another question going back to some of the work I think that the University of Minnesota did in classifying the stands. In your opinion, how well does the stand boundary process work for delineating stands with less than perfectly distinct boundaries?
And that is a great question, and I think that we will have a better answer for you in a couple of months. So what you saw there is what I've seen thus far. Keith Pelletier is actually going to deliver that data soon, either by the end of this month or soon after in December, and then we will do a analysis on how that process is working, and that's partly why we are doing other work alongside the university, like grid metrics that Ram is working on, or using open sourced software like R and others that Scott has been using to see if we can create stand boundaries in other methods. E-cognition is pretty expensive, and so that's one of our biggest concerns right now with with creating stand boundaries. How well does it work, and the cost. So I can get back to folks at a later date when we have more information on how those boundaries actually line up with what we're thinking.
And another question on, you mentioned R, Dennis. So what was the coding that was being done in R? And maybe I might ask you to go to that slide if you don't mind. What was the visual model in after the computation?
That's a good question, one that I can't answer, but maybe Ron can answer.
LiDAR package.
R package? LiDAR package. There. I don't know what the coding is. That's why it's called clever coding. It's LiDAR through R.
Great. And then another question about the average stand size. You had mentioned between 23 to 25 acres, I think.
Yes.
Does that reflect the type of disturbance or the soil unit? So maybe talk a little bit about those average stand sizes that you're seeing in the DNR data.
So that average stand size is in fact, John, who isn't here anymore, may be able to talk better about that. But that's basically what comes out of our CSA data, in that that's how we manage our stands. And in fact, I think it's just coincidental that the stand size ends up being in that 20 to 25 or 23 acres. Of course, we have larger stands, but it has a lot to do with disturbance and harvesting, or as Jennifer would say, fragmentation and parcelization.
Great. And then I see one more question. Do you have any preliminary accuracy assessment for field plots versus LiDAR estimates of stand characteristics, or is it too early for that?
So we have done some accuracy assessment on the field plots. I don't have anything formal written up. So we've done some assessment of what our interns collected. That would be Jason Lingenecker's responsibility. He's done some of that. And the way that we're looking at this is some of the field data will be used for an assessment of the accuracy of the stands or the objects that are created. So it's a kind of a twofold. Some of those stands will be used for imputation, and some of them will be used for an accuracy assessment. We would love to use the FIA data, and we may be able to use some of that, but our our biggest hang up with using FIA right now is that in those areas, the plot center is not tied or GPS to the sub-meter accuracy. And that's why we've used sub-meter GPSs in our 10th acre plot data collection. So that's forthcoming.
And then another quick question. Did you say that you were working on fuels characteristics as well, Dennis?
Well, I think that the first year we were collecting some information on fuels and downwarding debris. However, that is a metric that we can pull out of the LiDAR data using grid metrics. Ram would have to speak more to that than I can, but that is just one of the possibilities that we can pull out of high density LiDAR data.
And then another one, Dennis, can any LiDAR data be released for agencies in Lake County?
Yes, it should be released here in the next couple of months. I do have to speak with the Superior National Forest, but that should be released. Same thing with Chippewa. We just have to have a mechanism for distribution. So what we wanted to make sure that we could utilize that data, produce our metrics before we released it, and then at least by the end of the project, it will be released as data that's paid for by the state taxpayer and the national program.
Perfect. Well, thank you, Dennis, for answering all those questions, and thanks to everyone joining us. Really great questions. As you can tell, a lot of interest in this project that Resource Assessment is a part of. So thanks, Dennis, for sharing that with us today.
Yep.
I did want to remind you also, it looked like Madison Rodman with SFEC put a link to get continuing education credits. So those are available in the chat area. And then also we have a feedback form for today's webinar. If you wanted to fill that out, there's another link there. And so our webinar next week, or next month I should say, is on Tuesday, December 18th. And that's going to be talking about a fisheries perspective on timber sale design. So that'll be the next month's webinar in our forestry webinar series. And so with that, we'll sign off now. We will also have a recording of this, I should say, and we'll send that out probably within a couple of days to folks if they're interested in rewatching and sharing it with others that may not have been able to join us today. So with that, thank you again, Dennis, and we'll start signing off.
Thanks.